Right, so today we're going to look at vertical and horizontal asymptotes. So an asymptote is a line that a function approaches very, very closely, and this is called an asymptote. So it doesn't necessarily touch this line, it just gets really, really, really close. And it's good to keep in mind that the denominator of a rational function, so a function that's in terms of a fraction, cannot be equal to 0. We can't ever divide by 0. So if we're looking at finding vertical asymptotes, first of all, there's two kinds of asymptotes. There's vertical and horizontal. And if we're looking at finding a vertical asymptote, it's going to be when the denominator is equal to 0. So to find a vertical asymptote, we make our denominator equals to 0. It's a bit like the domain. Remember with domain, if we were trying to find this function, we said, if we were trying to find the domain of this function, we said, well, x minus 1 cannot equal 0. If we add 1 to both sides, we get that x cannot equal 1. So that's our domain. If we're trying to find the vertical asymptote, right, so if we're trying to find the vertical asymptote, we do what's written here. We're actually going to make our denominator equal to 0, and we get x equals 1. So notice the difference. Domain, x cannot equal 1, and that is because we have a vertical asymptote of x equals 1. If you think about the line x equals 1, that's a vertical line when x equals 1. So the vertical asymptote of this graph is going to be that point. Okay, horizontal asymptotes. Right, so that's vertical asymptotes. Horizontal asymptotes we find by looking at the behavior of the function as x gets larger and larger and larger, or basically as x goes to infinity. A little shortcut for this is something called Bobo button eats CC. And so what this means, okay, so Bobo stands for bigger on bottom is equal to 0. This button stands for bigger on top, none. And each CC means exponents are the same, divide coefficients. So it's a little, I guess, homonym for you to help remember horizontal asymptotes. This is only for horizontal asymptotes. So what this means, it all refers to powers of x. So it all deals with powers of x. So in this example above, example 1, if we look at the powers of x, so we have x to the power of 1 in the numerator and x to the power of 1 in the denominator. So exponents are the same. And it tells us divide coefficients. So if we look at the coefficients of x, we have 1 and 1. So we're simply, for a horizontal asymptote, we're going to divide our coefficients of x. So we're going to have 1 over 1, which is 1. Horizontal asymptotes are always of the form y equals. So our horizontal asymptote is going to be y equals 1. If you think about it, y equals any constant is going to give us a horizontal line. So y equals 1, that asymptote is going to be just above the x-axis. Okay, so that's for each DC. Exponents are the same. Bigger on bottom refers to the power on the bottom being larger. So for example, if we have something like x plus 2 over x squared minus 1, something like this. Bigger on bottom means the power of x is bigger on the bottom in the denominator. when that happens, our horizontal asymptote is going to be 0. And if we have something where our exponent is larger on the top, so something like this, something like that, so our exponent of x is larger on the top, so we've got 3, and we've got 1, it's bigger on top, therefore there is no horizontal asymptote. And exponents are the same. Just to give you another example, if we have something like 2x to the 4th minus 1 over 3, something like that, we've got the same. Exponents are the same. Our powers of x are the same. So we're going to divide our coefficients. Our coefficients are 2 and 3 of x. So we'll have y equals 2 over 3. Okay, so more practice. We're going to find the vertical asymptote and the horizontal asymptote. So again, to find the vertical asymptote, we're going to make our denominator equal to 0. So x minus 1 is equal to 0. If we add 1 to both sides, we get x equals 1. To find our horizontal asymptote, we look at our powers of x. We can see our exponents are the same. So exponents are the same, divide coefficients. That's kind of what we're thinking in our head. So our coefficients here are 1 and 1 of x. So we'll have y equals 1 over 1, or in other words, y equals 1. So we have our vertical asymptote at x equals 1, and our horizontal asymptote at y equals 1. Okay, example 2. For our vertical asymptote, again, we're just going to make the denominator equal 0. So x plus 3 equals 0, we'll minus 3, and we get x equals negative 3 as our vertical asymptote. Our horizontal asymptote, we can see again our exponents are both 1, so exponents are the same. Divide coefficients. Our coefficients are 2 over 1. So we've got y equals 2 over 1, or in other words, y equals 2. Because 2 divided by 1 is 2. Okay, example 3. For vertical asymptote, we take our denominator, make it equal to 0. We can add x, and we get x equals 4. Okay, and then our horizontal asymptote. Don't be fooled here because the x isn't our first term, but that's okay. So we've still got x to a power of 1 in the numerator, and look, it's still to a power of 1 in the denominator. Our coefficients are 1 and negative 1. So exponents are the same. Divide our coefficients. We get y is equal to 1 divided by negative 1, or in other words, y equals negative 1. Okay. Here we actually have to combine these into one fraction in order to apply these rules. So we'll have to multiply 2 by 3x plus 2 and divide by 3x plus 2. So we'll have 2 times 3x plus 2 plus 2 all over 3x plus 2, which gives us 6x plus 4 plus 2 over 3x plus 2. We get 6x plus 6 over 3x plus 2. Okay, so vertical asymptote 3x plus 2 equals 0, minus 2, 3x equals negative 2, and divide by 3, so x equals negative 2/3. Okay. Okay, and our horizontal asymptote. So if we look, again, our exponents are both 1 of x, so exponents are the same, again. And we're going to divide our coefficients. So if we do y is equal to 6 divided by 3, we'll get y equals 2. Okay. Okay, here we're going to find all asymptotes. So again, we're going to find our horizontal asymptotes and our vertical asymptotes. So vertical asymptote, we're just going to make the denominator equal to 0, and that's it. Our vertical asymptote is x equals 0. The horizontal, so we're thinking about exponents of x. In the denominator, we have 1. In the numerator, is actually x to the 0, or just 1. So it happens that our powers of x are bigger on the bottom. So bigger on the bottom, our horizontal asymptote is 0. So y equals 0. Okay, here our vertical asymptote is going to be x minus 1 equals 0. When we add 1, we get x equals 1. Horizontal, we've got powers of 1 for our x, so our exponents are the same. We're going to divide our coefficients. Our coefficients are 2 in the numerator and 1 in the denominator. So y equals 2 over 1, or y equals 2. Okay, here we've got a vertical asymptote. We'll have x minus 4 equals 0. When we add 4, we get x equals 4. As our vertical asymptote. Horizontal, we look at our powers of x. We can see they're both 1. The coefficients are also 1, so exponents are the same. Divide our coefficients, we get y equals the exponents, which are 1 over 1. Or sorry, not the exponents, the coefficients, 1 over 1, and y equals 1. Okay. That's just a reminder of what the horizontal asymptote is below. More asymptotes. Okay, we've got 1 over x squared. So for the vertical, we'll make our denominator equal 0. So x squared equals 0. We can square root both sides, and we get x equals 0. We don't need the plus or minus because 0 is neither positive nor negative. So vertical asymptote is x equals 0. Horizontal, again in the numerator, we basically have an x to the 0. So it happens that our power is bigger on the bottom, so y equals 0. Okay, here our vertical asymptote is x minus 2 equals 0. We add 2, we get x equals 2. And the horizontal asymptote, again we have x to 0 on the top, x to 1 in the denominator, so again our power of x is bigger on the bottom, so y equals 0. Okay, we'll have to combine these into one fraction, so we'll need a common denominator. So we've got 10 minus 2x, 3 over 5 minus x, or 13 minus 2x over 5 minus x is our function. Okay, so vertical asymptote, we've got 5 minus x equals 0. If we add x, we get x equals 5. For our horizontal asymptote for that same one, we've got our exponents are the same, they're both to the power of 1. So exponents are the same. Divide coefficients. We've got a coefficient of -2 over -1. So y equals -2 over -1, which is 2. So our horizontal asymptote is y equals 2. Okay, last one on this page, we've got a vertical asymptote of x minus 2 equals 0, which means x equals 2. And horizontal asymptote is going to be, our exponents are the same. We've got an exponent of 1 and an exponent of 1. Exponents are the same, divide coefficients. So we've got a coefficient of 1 and a coefficient of 1. So y equals 1 over 1 for y equals 1. Okay, so now we're going to put it all together. What does this all mean? Now that we've found these asymptotes, what does this look like? How does this help us? What information does this even give us? So we're going to look at how do we even graph rational functions, and how does domain, range, and sign analysis help us to do that? So we're going to put it all together. So let's first find the asymptotes. So find all asymptotes first. So in this one, we're going to find our vertical asymptote, which means that our denominator is equal to 0, or just x equals 0. Our horizontal asymptote, we've got x to the power of 1 in the denominator, x to the power of 0 in the numerator. So we've got a bigger bottom situation, which means y equals 0. Okay, so if we're graphing this, we've got our graph here. And what we just found is that we've got a vertical asymptote at x equals 0, which we represent with a dashed line. And we have a horizontal asymptote at y equals 0, which again we represent with a dashed line. Okay.
I need to get you back. I have.
Okay, right. So we've got our vertical asymptote at x equals 0, horizontal asymptote at y equals 0. We're going to do sign analysis of this function. We talked about sign analysis before, and we always put our zeros on the axis that we created, right? And I don't know if you remember, but I also said that you'll put vertical asymptotes in as well. So zeros and vertical asymptotes go in your sign analysis. So we have to figure out, okay, this function doesn't have any zeros. Can 1 over x ever equal 0? Well, no, because then we get 1 equals 0 when we multiply x over, and that doesn't actually make sense. So there's no zeros of this function. This function never touches the x-axis. But we do have a vertical asymptote, and we do that again with a dashed line as sign analysis. So we have a vertical asymptote at 0. We're going to do sign analysis of this function. We're going to choose a number less than 0 and plug it in for x. So for example, -1. If we plug -1 into our function, we're going to have 1 over -1, which is going to give us a negative number. Then we can choose a number greater than 0. For example, 1. We'll have 1 over 1, which is a positive number. Or remember I said if your zeros are to an odd power, or your vertical asymptote in this case is to an odd power, it's going to alternate. So we're going to go from negative to positive. Okay, so what that means on the graph is that our function is going to be totally below the x-axis. It's going to be negative when x is less than 0. So when x is less than 0, our function is going to be below the x-axis. We've got our function, it's following the x-axis because of our horizontal asymptote, and it's following the y-axis here because of our vertical asymptote. This positive tells us that our function is above the x-axis from 0 to infinity, when x equals 0 to infinity. So we know it's going to be somewhere in here. Again, we know it's going to follow our vertical asymptote and our horizontal asymptote. So we get something like this. Okay, next. Next we've got this function here. We're going to find our vertical asymptote. X minus 1 is equal to 0. We're going to add 1, and x equals 1. To find the horizontal asymptote, we can see that our exponents are the same. We're going to divide our coefficients, so we've got a coefficient of 2 over 1, or y equals 2, is our horizontal asymptote. So what that looks like on our graph, we've got a vertical asymptote at x equals 1, so x equals 1, and we've got a horizontal asymptote at y equals 2. This is 1. Okay. And then we need to do sign analysis of our function. Sign analysis. We're going to look for any zeros, and we're also going to put our vertical asymptotes into that function. So we know we have a vertical asymptote at 1. We're going to use a dashed line to represent that. To find the 0, we're going to make the numerator equal to 0. So 2x plus 1 is equal to 0. We can minus 1 to the other side. We get 2x equals negative 1. Divide by 2, x equals negative 1/2. Okay, so we know we've got a 0 at negative 1/2. So we put that into our sign analysis. Okay, we can choose a number between 1 and negative 1/2. 0 is quite nice. And we can plug that into our original function. So we're doing 2 plus 0, 2 times 0 plus 1 divided by 0 minus 1. So 2 times 0 plus 1 divided by, what was it, 0 minus 1. And that gives us 1 over negative 1, which is a negative number. So this is negative. Again, we can look at our 0, which is this 2x plus 1, and we can see we've got x to the power of 1. Our 0 is just to an odd power, which means it's going to alternate around our 0, our sign analysis, and also our vertical asymptote is to an odd power. Therefore, it's going to alternate here as well. So we know our function. We've got this 0 at negative 1/2. And we know our function is going to be positive and then negative. And then we know it's going to, again, be positive. So it's going to hug these kind of asymptotes. So it's going to hug our horizontal asymptote until negative 1/2, and then it's going to hug our vertical asymptote. So notice it crosses the x-axis at negative 1/2 and then becomes negative. And here, when x is greater than 1, it's going to hug our vertical asymptote and then hug our horizontal asymptote. So we get something like this as our function. It also asks us to look at the domain and range. So domain for this function is going to be that x can be all real numbers except 1, so x cannot equal 1, and range is, if you look, y doesn't equal 1. Or no, y doesn't equal, what is that, 2. Y never actually touches 2. We can do the same with the one before. Here we've got, for domain, x doesn't equal 0, and range is y doesn't equal 0. Let's see. Okay, this function here. I think this is the last one. Yeah. Okay, so we're going to look at, again, how do we graph this function? We've got a vertical asymptote when x minus 4 equals 0, which means x equals 4 is our vertical asymptote. Horizontal asymptote is our exponents are the same. So we're going to divide our coefficients. Our coefficients are 1. So we've got y equals 1 over 1, which means y equals 1. So y equals 1. Okay. What does that look like in terms of a graph? So we've got our horizontal asymptote at y equals 1, our vertical asymptote at x equals 4. See, that's 4. Okay, we need to do sign analysis, and we need to find any zeros of our function first. So we make the numerator equal to 0, and we get x equals -2 is the 0, which means on our sign analysis, we're going to have -2, and we're going to have our vertical asymptote, which we'll represent with a dashed line, at 4. Then we'll do sign analysis of this function. So we'll plug in a number between -2 and 4. If we plug in 0, we have 0 plus 2 over 0 minus 4, which is going to give us a negative number. And we know this is going to alternate because our 0 is to an odd power, and our vertical asymptote is to an odd power. So that means we're going to have, we've got our 0 at -2. Our function is going to be positive and hugging the horizontal asymptote, and then it's going to go negative and hug our vertical asymptote. Then it's going to be positive, hugging both asymptotes. Okay, and that's it for today. So thank you very much. Have a good rest too.